Apologies for the delay due to some technical issues. So welcome to the fourth day of a one-week online FDP on antennas for 5G communication and beyond. And today is the UWB antenna design using hands-on experience. Okay, so I'm delighted to introduce Dr. DVN Koteswarao sir. He has received his BTech degree in Electronics and Communication Engineering from Nagarjuna University, Andhra Pradesh, and MTech degree in Systems and Signal Processing from JNTU Hyderabad. He has obtained his PhD degree in the field of wireless communications from the Department of ECE, JNTU Anantapur, Andhra Pradesh. Currently, he is working as an associate professor in the Department of ECE, Aditya Engineering College, Surampalam, Andhra Pradesh. He has 16 years of teaching and 1 year industry experience. He is a member of IEEE. He has published more than 40 international national journals and conferences in various SCI, SCIE, ESCI, Scopus Index journals. And also he acted as a reviewer for various SCI, SCIE, Scopus Index journals like International Journal Electronics, International Journal of Electronic Letters, AEU, International Journal of Electronics and Communications, Analog Integrated Circuits and Signal Processing, Microwave and Optical Technology Letters, International Journal of Communication Systems, and International Journal of Microwave and Wireless Technologies, and so on. He is qualified as Assistant Professor in UGC NET in July 2016. He is having 246 Google Scholar citations with H index of 9 and I-10 index of 9. His research interest on design of microstrip patch antennas, UWB antennas, MIMO, CMA, metamaterial, flexible and multi-band antennas. Without further any delay, I request Dr. DVN Koteswarao sir to start the session. Thank you. Sir, you are muted.
Sir, thank you, sir. Thank you for your introduction, sir. So, first of all, I would like to say sorry for inconvenience due to technical problem to all the participants. So, I am very happy to be a part of this one-week online FTP on antennas for 5G communications and beyond. I'm thankful to the chief patrons, Dr. N. Shesha Reddy Garu, Chairman, Dr. N. Satish Reddy Garu, Vice Chairman, Patron, Dr. M. Srinivas Reddy Garu, Principal, Advisory Committee, Conveners, Coordinators, and Organizing Committee. Thank you, one and all. So today, I would like to discuss about the fundamental planar UWB monopole antenna designed by using computer simulation technology software. So myself, Dr. DVN Koteswarao, Associate Professor, Department of ECE, Aditya Engineering College, Surampalam, Andhra Pradesh. The contents I want to cover as part of this presentation are introduction, ultra-wideband antenna, introduction, ultra-wideband antenna, advantages and applications of ultra-wideband antennas, computer simulation technology software, UWB antenna designs. So for the first 15 minutes of this presentation, I would like to discuss about the fundamentals regarding antennas and antenna parameters, followed by what is the importance of ultra-wideband, what is an ultra-wideband antenna, their advantages and applications, then computer simulation technology software, the installation procedure, and finally hands-on experience on to design an ultra-wideband antenna design. Coming to the introduction. An antenna, according to IEEE, Institute of Electrical and Electronic Engineers, the definition of an antenna is a means for radiating or receiving radio waves. And an antenna is a metallic apparatus for sending and receiving electromagnetic waves. The ultra-wideband antenna, which we are going to focus in this presentation, is made with microstrip patches. So that, first of all, we would like to know what is microstrip patch antenna. So a microstrip patch antenna is a radio antenna. Mostly it is used at microwave frequencies. Typically they are ranging in gigahertz. We know, according to IEEE standards, the microwave frequency bands have been defined L, S, C, X, Ku, K, Ka, millimeter, submillimeter over the range of frequencies of 1 to 2, 2 to 4, 4 to 8, 8 to 12, 12 to 18, 18 to 27, 27 to 40, 40 to 300 and greater than 300 gigahertz of frequencies. Because the ultra wideband antenna in this session, I'm going to discuss as a microstrip patch. We should know what is the structure of the microstrip patch antenna. So this is the structure of a microstrip patch antenna. It is consisting of a dielectric substrate, and the thickness of the dielectric substrate is assumed to be, or height of the dielectric substrate is assumed to be h. And on top of this dielectric substrate, we have to deposit h, a patch structure. Let us say here a rectangular patch is available whose width is assumed to be W, length is assumed to be L, and thickness is assumed to be small t. Depending upon the shape of this patch structure, we can name the antenna. If it is a rectangular type, then it is rectangular shaped microstrip. If it is a square, it is square shaped antenna. And if it is some slotted type, then it is slotted type of antenna likewise. And at the bottom side, we have the ground plane. The ground plane and the patch structure are generally copper materials, and the dielectric material is various types of materials have been used depending upon our application has been intended. If it is needed for wireless body area network applications, means we need some bending and horizontal direction and vertical direction. In such a case, some flexible dielectric substrates have been taken. Otherwise, in most of the cases, the low cost FR4 substrate material can be used. Coming to advantages of microstrip antennas, the microstrip antennas are lightweight and low volume. And if you are going to choose a low cost substrate material like FR4, the fabrication cost is low, and hence we can manufacture them in large number of quantities. And because if you can support a planar type of structures, then those can be integrated with various other circuits which are available in integrated form. Hence, we can easily integrate such type of microstrip patch antennas with other circuits in a system. And microstrip antennas can capable of providing dual triple frequency band of operations. Coming to antenna parameters, the ultra wideband antenna has been analyzed. We have to observe these are the parameters for understanding the behavior of ultra wideband antenna. So they are reflection coefficient and VSWR, radiation patterns, radiation efficiency, directivity and gain, group delay and transfer function. Group delay and transfer function are time domain characteristics, whereas reflection coefficient and VSWR, radiation pattern, directivity, gain, all these are frequency domain characteristics. Coming to the reflection coefficient and VSWR, let us consider an electrical source which is connected to a load like an antenna through a transmission line. When a power is to be transmitted from source to antenna, if that antenna is not perfectly matched to the transmission line, it will cause some reflections have been taken place and some amount of power has been reached from load to source, and that is considered to be reflected power. And inside the transmission line, the combination of incident wave and reflected waves can create standing waves. Now, what is meaning of reflection coefficient is, it is representing how much amount of power is reflected back towards source from the antenna. And it is given by mathematical equation as modulus of rho equal to ZL minus Z0 by ZL plus Z0. Here ZL is the load impedance and Z0 is characteristic impedance or free space impedance, and generally it is equal to 377 ohms. Here ZL is nothing but antenna impedance or load impedance. Coming to VSWR. VSWR is a measure of the amount of impedance mismatch that should be taken place in between the source and the antenna input terminals. And that is expressed in terms of reflection coefficient as VSWR equal to 1 plus rho by 1 minus rho. And the ideal value of VSWR is 1. And the practical value of up to 2 is considerable. So VSWR in between 1 to 2 is to be considered for an antenna for all practical applications. Next, coming to radiation pattern. The radiation pattern of an antenna is nothing but a three-dimensional graphical representation that represents the variation of field or power as a function of spherical coordinates r theta and phi. There are three types of radiation patterns: isotropic radiation pattern, directional radiation pattern, omnidirectional radiation pattern. An isotropic radiation pattern is a pattern that can radiate equally in all directions, but it is not possible practically. It is a hypothetical antenna. And coming to directional radiation pattern is a pattern that can direct radiation along a particular direction. And omnidirectional radiation pattern is a radiation pattern that is non-directional in the given plane and direction in its orthogonal planes. So depending upon applications, we are going to get from an antenna either directional radiation pattern or omnidirectional radiation pattern. In case of high accuracy radars and biomedical imaging systems, we require directional type of radiation patterns, whereas in the case of mobile applications, we have to use omnidirectional radiation patterns. Next, coming to radiation efficiency, and it is defined as the ratio of total power radiated by the antenna to the net power accepted by the antenna from the source. And directivity of an antenna is defined as the ratio of radiation intensity in a given direction from the antenna to the radiation intensity which is to be averaged overall all the directions from the antenna. And once we know radiation efficiency and directivity, the gain is evaluated by radiation efficiency into directivity. The gain is a practical parameter, whereas directivity is an ideal parameter. Always directivity is greater than gain. Coming to the important characteristics of ultra-wideband antenna in time domain, which are group delay and transfer function. And what we are expecting from an ultra-wideband antenna is a minimum amount of pulse distortion. To achieve such type of minimum amount of pulse distortion, it must have to satisfy a flat group delay whose group delay variations are less than 1 nanoseconds, and the transmission loss in between two antennas which are placed in side by side and face-to-face arrangements are less than minus 30 decibels. Now, I would like to discuss what is group delay. Is the rate of change of transmission angle with respect to frequency is called as group delay. Mathematically, it is expressed as tau g equal to minus del phi by del omega. And the group delay variations, whenever they are exceed greater than 1 nanosecond, it will produce the phases are to be non-linear. Whenever the corresponding group delay variations are less than 1 nanosecond, the phases will be a linear type of manner. And similarly, the transmission loss between the two antennas which are in side-by-side and face-to-face arrangements, whenever they are minus 30 dB, we obtain a linear type of phase characteristics. So these are very important in the case of ultra-wideband antenna design. So flat group delay and transmission loss less than minus 30 dB, which ensures a linear type of phase response. Coming to our topic, ultra-wideband antenna. So in 2002, the US Federal Communication Commission, FCC, assigned an unlicensed frequency spectrum of 3.1 to 10.6 gigahertz for ultra-wideband applications. Within this particular band, 3.1 to 10.6 gigahertz of frequency, there are various narrowband systems are already existed, such as WiMAX, wireless interoperability for microwave access, ranging from 3.3 to 3.6 gigahertz, C-band operating from 3.7 to 4.1 gigahertz, aeronautical radio navigation band, ARN band, ranging from 4.1 to 4.5 gigahertz, lower WLAN, lower wireless local area network band operating from 5.15 to 5.35 gigahertz, upper wireless local area network band operating from 5.725 to 5.825 gigahertz, IEEE INSAT C band operating from 6.7 to 7.1 gigahertz, downlink of X band ranging from 7.25 to 7.75 gigahertz, and ITU band, International Telecommunication Union band, which is ranging from 8.1 to 8.4 gigahertz. So all these bands as a part of ultra wideband frequency, which is to be ranging from 3.1 to 10.6 gigahertz. An ultra wideband is a radio technology where that can generate a very short duration of electromagnetic pulses, because those pulses are short in time domain. When they are converted into frequency domain, they are having a very wide spectral characteristics, wide frequency spectrum. That is the reason why this technology is named as ultra wideband. And it is very much useful, and it can make use only a very low energy level. Typically, the energy level used by UWB for transmitted power is minus 41.3 dBm per megahertz, and it is used for short range, high bandwidth communications over a large portion of the radio spectrum. What is the advantage of ultra wideband? And we can understand that one with the help of Shannon's formula for data rate. The channel capacity or data rate, which is given by Shannon's formula, given by C equal to B log base to 1 plus SNR. Here the channel data rate is depending upon two factors. One is bandwidth and another one is signal to noise ratio. To increase the value of channel capacity or channel data rate, either we have to increase the bandwidth or we have to increase signal to noise ratio. But it is not recommended to increase the value of signal to noise ratio, because of we are going to use always portable devices like mobile phones and laptops. Whenever we are going to use such type of portable devices, and we are increasing this SNR value, it is harmful to human body. That is the reason why it is recommended to increase bandwidth only for the purpose of increasing channel data rate. That is the reason why ultra wideband plays a very important role to increase the data rate. And next, for narrowband systems, the absolute bandwidth is less than 10%, whereas for ultra wideband systems, the absolute bandwidth is approximately 110%. Now, methods to improve bandwidth of an antenna. How we can convert a narrowband into a wideband, or ultra wideband, or super wideband, or extremely high wideband is, from the literature, it is possible increase the bandwidth by increase of substrate height and by making use of defected ground structures. Along with defected ground structure in literature, mostly we have used etching of slots in patch and ground structure, and we have included round shapes types of structures and using tapered feed. So increasing of substrate height causes increase the dimension of the device. That is the reason why it is not mostly used. And the most used techniques are use of defected ground structures, etching of slots in patch and ground structures, including of round shapes, and using tapered feed type of structures. And next, coming to the requirements of UWB antennas. While designing UWB antennas, you must be taken care about these points. The fractional bandwidth must be greater than 500 megahertz. What is fractional bandwidth is FH minus FL by FC, where FH is upper cutoff frequency or minus 10 dB frequency of radiation bandwidth, and FL is lower cutoff frequency. FC is center frequency, where that center frequency is equal to FL plus FH by 2. That is fractional bandwidth equation is 2 into FH minus FL by FH plus FL. So that should be greater than at least 500 megahertz for ultra wideband antennas. And then ultra wideband antennas must have a low profile, low cost, and they are in miniaturized in size to get to embed and easy to integrate with other circuits. And we have miniaturized the ultra wideband antennas with other type of structures like metamaterial concept, and then omnidirectional radiation characteristics for mobile applications. As I told in the previous slides, we required omnidirectional type of radiation patterns for mobile applications, and directional radiation patterns are required for high accuracy radars and imaging systems. And another important parameter is high radiation efficiency is required. Typically more than greater than 90% is required for the purpose of ultra wideband antennas. And coming to the time domain behavior of UWB antenna, to achieve that one, I already discussed, we need to get a linear type of phase characteristics. For that, we have to get the value of group delay is almost constant, or group delay variations are less than 1 nanosecond, and isolation must be less than minus 30 dBs. Coming to the advantage of ultra wideband antennas, as it covers a wide range of frequency from 3.1 to 10.6 gigahertz. It can show wide operational bandwidth characteristics. And as it is having a large value of bandwidth, according to Shannon's formula, I told you, it is offering maximum channel capacity or data rate and high data transmission rate at low power of minus 41.3 dBm per megahertz is possible. And in case of ultra wideband, we got multiple number of resonances. So multi-band performance is possible. In stability, we can achieve stability with the help of the flat type of group delay. And also we require less variation in the gain characteristics in frequency domain for an ultra wideband antenna design, and low fabrication cost. If you are going to design this one with microstrip patch antennas, especially with FR4 substrate, we can achieve the task. And coming to applications of UWB antennas, they are used in tracking and position location systems. Say, they are used in biomedical imaging systems. Recently, one paper is published by myself. A compact SCDGS tapered fed notch UWB antenna integrated with KU K-band for breast cancer detection. So in such a case, we can make use an ultra wideband antenna, and a pair of ultra wideband antennas have been placed on either side of created breast phantom in CST software, and you can notice a considerable difference in between the values of S21 between a free space phantom only design and phantom with tumor, and the same is identified, the tumor is identified with the help of imaging results like SAR, specific absorption rate. With the specific absorption rate without tumor condition and with tumor condition, we can identify the tumor location very clearly with the help of ultra wideband antennas. Why ultra wideband antenna is supported to clear distinguish of tumor location is because of its characteristics of ultra wide bandwidth. The signals have been penetrates more depth into the body, and also the signal penetrates more, and also because of wide frequency spectrum, data rate is high, so that we got more clarity images. Come back. This is another application, wireless body area network. So to know to detect skin cancer detection, and also used in tumors which are available in brain, etc. For all those applications for tracking and position location of all those tumors, we can make use ultra wideband antennas. And coming to communications used in IEEE 802.15.3s wireless systems such as M3 3 players, desktop PCs, audio CDs, DVDs, VCRs, mobile phones, digital TVs, digital cameras, removable hard disk can make use ultra wideband antennas. I would like to show such type of devices in the next slides. And coming to radars, so used in through wall imaging systems and ground penetrating radar for the purpose of detection of any soil or water information, or if any person is trapped inside a building due to earthquakes, etc. So these are some of the antennas which have designed various researchers. This is one of the ultra wideband antenna which is designed, and this is the simulation model in CST software. And here it is consisting of the skin layer outside and the breast tissue and then a tumor. And to know about whether a tumor will be presented or not, it is analyzed with the help of S21 parameter and with the help of specific absorption rate. So the designed antenna have been taken on either side of this breast phantom in the simulation setup model. From the values of S21 and SAR, it is possible to detect whether a tumor will be presented or not. And then this is another antenna which is to be developed by the researchers for the purpose of detection of skin cancer, etc. So here, this antenna is U-shaped type of antenna where it is included with swastik type of slot and a defected rectangular defected ground structure. And this is the simulation skin phantom structure in CST model. And by placing that one antenna, different conditions touching with body and some distance with body, the results have been reported by the researchers for the purpose of detection of skin cancer. And these are the applications which are used with ultra wideband technology in communications, like Samsung Galaxy S21 Ultra, Galaxy S21, iPhone 11 series, etc. All these will make use ultra wideband technology for the purpose of high data rates. And these are the third mentioned application, radars. The basic principle is here, radar principle, radio detection and ranging. So in radio detection and ranging, we have to transmit signal to the object, and the signal has been intercepted by the target and it is reflected back. And from the information received by the receiver, from that reflected signal, we can identify what type of object that is. So here one example is shown. One victim who is trapped under a collapsed building due to earthquakes or due to some different considerations. So we have to use this ultra wideband technology. Coming to through wall imaging system, here also on one side of antenna we have to place beside the wall, and we have to locate the human body is presented on other side or not, or any object is presented. With the help of reflection obtained from those signals, we can identify that whether body is presented or a metal is presented on either side of the wall. Coming to research scope on ultra wideband. So ultra wideband, there is a lot of work is done already on ultra wideband, where several antennas have been designed from 3.1 to 10.6 gigahertz. And also ultra widebands have been designed with notch characteristics also. That is also almost saturated. 1 band notching, 2 band notching, 3 band or 4 band notching, etc. There is a scope right now making use of this ultra wideband is possible with MIMO technology. So we can extend this ultra wideband as a MIMO with 2 elements, 4, 8 elements, etc. for the purpose of to enhance the data speeds, channel capacity, and range of communications. And also, as I said, the notch characteristics with single, double, triple, and quadruple band notch characteristics, you can get more number of literature. But there is something scope is there to achieve penta and sextuple band notch characteristics for ultra wideband antennas, where I have already specified that in ultra wideband frequency, we have various narrowband systems are already existed. Typically, there are 7 to 8 number of narrowband systems are existed. So WiMAX, C band, ARN band, lower WLAN, upper WLAN, IEEE INSAT C, downlink of X-band ITU, so that there is a scope to extend ultra-wideband antennas with band notch characteristics with going for penta, sextuple, or more number of notch characteristics. And then design of reconfigurable band notch ultra-wideband antennas by using varactor diodes, MEMS, and pin diodes is also another scope to do on ultra-widebands. And we have to integrate the ultra-wideband with low frequency bands such as Bluetooth band, global system for mobile communication, GSM band, global position system, GPS, or we have to integrate ultra-wideband with K band, Ka band, or millimeter wave bands for the purpose of increasing data rates. And also for the purpose of achieving miniaturization of ultra-wideband, metamaterial concept will be there. Coming to CST software, because my intention as part of this presentation is to discuss the design procedure of ultra-wideband antenna using CST software. So a CST Studio, Design Studio software is a high performance 3D electromagnetic analysis software package, and that can be used for the designing, analysis, and optimizing the electromagnetic components and systems. This computer simulation technology software is depending upon FIT, finite integration technique, and it is also popular among antenna designers due to ease of design and simulations. And in HFSS, we need to design the environment like radiation box in our own, and it is to be assigned for the design structure. But whereas in case of CST, automatically the radiation box will be provided by CST. And for microwave tube design, generally mostly preferred one is CST software. And CST software is most user friendly. The navigation tree structure of the CST is easy to understand for someone who is not familiar with the person who is not more expertise in RF domain. So for the beginners of antenna design engineers, computer simulation technology is better for the purpose of designing of antennas. Simulation time is less, and it is available with time domain solver also. And then these are the system requirements for DS Simula CST Studio Shoot. For installation of this DS Simula CST Studio Shoot, you can require the operating system list of Windows 7, 8, 8.1, 10. RAM memory of 2 GB of RAM is required. Hard disk space of 7 GB at least. And especially when you are going for biomedical imaging applications like detection of tumors in brain, definitely we require a large amount of hard disk space. And processor like Intel dual core processor or later is required. And this is the installation procedure for student version of CST 2021. So if you have any problem regarding this installation, I'd like to discuss the installation process later personally. And this is the flow chart of ultra wideband antenna design. So here, first we have to design a patch and ground structure along with a selected substrate material depending upon application. So if you are going for a microstrip antenna for ultra wideband applications, then mobile applications, etc. Then you can take a low cost FR4 substrate. But if you are going for biomedical imaging applications such as, you can make use of different types of flexible type of materials, roses, arduduride, etc. And after designing of this patch and ground structure, we have to simulate the structure in computer simulation technology software. And you can tune the dimensions of patch and ground until we have to achieve our required bandwidth. In this case, the ultra wide band, which is to be ranging from 3.1 to 10.6 gigahertz. If that bandwidth is not achieved, tune the dimensions of patch and ground. If it is achieved, then you can go for antenna fabrication and measurement. So these are the basic equations which are available in various literature for the purpose of design of rectangular patch antenna and circular patch antenna. I would like to move very quickly to discuss about these things. In this case, the design specifications are, first we have to choose the frequency, resonant frequency. If not, say for example, if I want to design an antenna which is to be operate for Wi-Fi of 2.4 gigahertz, then if not equal to 2.4 gigahertz, we need to choose. Then choose the substrate material appropriately. It is depending upon if you are going for low cost, that is FR4 substrate material is to be preferred. And choose the relative permittivity of the substrate. So epsilon R value is to be selected. And suppose FR4 substrate, typically this value lies around 4 to 4.5. And then choose the height of the substrate. So the height of the substrate, I already told you, for the purpose of increasing bandwidth, the height of the substrate is one parameter, but not recommended to increase much the height of the substrate, because we have to use these antennas in mobile or portable applications. So once we have decided the resonant frequency F naught, choose in the substrate material epsilon R value and H. Then for the rectangular microstrip patch antenna, calculate the width value by using this equation. Here, C is the light velocity. F naught value is already selected. And then epsilon R is relative permittivity of the substrate material. You have chosen already, so that you get the value of W. And then second step, we are going to calculate effective dielectric constant epsilon effective, which is given by using this formula epsilon R plus 1 by 2 plus epsilon R minus 1 by 2 into 1 plus 12 into H by W whole power minus 1 by 2. Here, epsilon R, again, permittivity, and H is height of the substrate, W is obtained from step 1, so that you got epsilon effective. And in case of rectangular microstrip antenna, due to fringing effect, the length of the patch structure will be changed, so that we need to calculate the effective length and the extension length delta L. By using these formulas, we can calculate L effective and delta L. Then we are going to calculate the actual length of the patch with the help of L equal to L effective minus 2 delta L. For all these parameters I had discussed. Now, coming to design of circular patch antenna. So to design the circular patch antenna, again we are going to choose the resonant frequency FR for which the antenna is to be operated, and then you are going for choose the dielectric constant epsilon R value of the substrate, choose the height of the substrate H. With these design values, we can calculate what about the radius of the circular patch by using this formula, which is given in this paper, and that is given by A equal to F by 1 plus 2H by pi F epsilon R into logarithm of pi F by 2H plus 1.7726 whole power 0.5, where this F value is calculated by using 8.791 into 10 power 9 by FR into square root epsilon R. Already you know epsilon R value, and you have chosen already FR value, so that you got F value. Once you know F value, you know H value already chosen, epsilon R value, you can calculate what about the radius of circular patch. Likewise, you have design equations for elliptical patch also there, but these are given for a single resonant frequency. But in the case of ultra wideband, we got multiple number of resonant frequencies, not a single frequency. That is the reason why to obtain that multiple resonant frequencies, so those single or individual resonant frequencies are staggered to produce ultra wideband. So to produce that ultra wideband, we have to introduce some slots in the patch structure or ground structure, or we have to use a tapered type of microstrip line feed structure, as I had discussed in the previous slides. Now coming to UWB antenna designs, so that I want to show you hands-on with the help of computer simulation technology software. So this is the one of the design I would like to show you by designing this antenna in computer simulation technology, where this design is taken from one of my paper published in International Journal of Electronics SCI Indexed Journal. So this is the paper here. So actually this antenna used to be designed for ultra wideband with quadruple band notch characteristics. So first we need to obtain ultra wideband characteristics which are ranging from 3.1 to 10.6 gigahertz. And after that I have introduced some band notch elements to eliminate interference with the existed narrowband systems within the UWB spectrum. So those are the band notch elements where I can show here. Two slots have been introduced to notch two bands. One via element is connected from top of the patch to ground structure, and these are the symmetrical split ring resonators have been taken. So first of all, I would like to design this ultra wideband antenna structure here in different steps. I designed this antenna. In the first case, it is available with a rectangular type of patch, and then at the bottom side, notches have been introduced, square type of notches have been introduced for the purpose of increasing bandwidth. Even we are introduced such type of notches, as I cannot achieve the required ultra wideband, what I'm going to do in the design is bevels have been introduced at both sides of the defected ground structure. So this is the parametric study I have made to obtain those results in CST software. So here antenna 1, antenna 2, antenna 3 results have been kept there. So what it is, antenna 1 is simply rectangular structure with rectangular defected ground plane. What is antenna 2 is with rectangular defected ground plane with at the bottom side square notches. And what is antenna 3 is the proposed ultra wideband antenna. So when bevels have been introduced at defected ground structure also. Now verify the results here. For the first antenna 1, that is blue color line, I got a very narrow bandwidth which is typically ranging in between 3.5 to 6, so that I am going to enhance the bandwidth to reach the ultra wideband, and that is one of the possible optimization has been done for the antenna by making notches at the bottom side of the rectangular patch structure. Now for the red line, the bandwidth is typically it is increasing, is noticed from this return loss plot, and is typically from 3 to almost 8 gigahertz. Even I cannot achieve the ultra wideband, so that what I have done for antenna design 3 is I have introduced bevels for the ground structure. So after bevels have been introduced for the proposed ultra wideband antenna, the bandwidth is drastically increased from typically 3 to more than 13. So this is one of the design I would like to cover as part of this hands-on experience by using computer simulation technology software. And this antenna covers in between 2.95 to 13.12 gigahertz. Here the front view and back view of the antenna have been shown. The yellow color one is a substrate material, and the red color one representing patch, and the green color representing ground structures. And if time permits, I would like to discuss the circular slotted ultra wideband antenna, which also designed by myself, and it is published in International Journal of Electronics Letters. And this antenna covers in between 2.99 to 16.65 gigahertz. And this is the antenna structure, where the patch structure is consisting of multi circularly slotted type of structures. along with some ellipses, like seems to be like a fan. So I can name that one as a navel fan shape. So depending upon the type of patch structure, we can name that antenna generally. And this is a microstrip line feed structure, and yellow one is again substrate, green one is ground material. And this is another antenna where I had designed, which is published in Progress in Electromagnetic Research. This is the combination of some ellipses. 3 ellipses have been added, some round shapes have been added to obtain the required patch structure. And defected ground structure, rectangular type of defected ground structure, once again taken here. As I already told you in the previous slides, for the purpose of increasing bandwidth, it can make use of defected ground structure. So I can make use in all those designs defected ground structure. So in the second design, I can make use slots have been introduced in the patch and ground. And then in the third design, I have introduced round type of shapes like ellipse shapes have been combined together where they can produce an ultra wideband bandwidth. So these are the 3 antennas I would like to give you an hands-on experience in the next session after break. Before that, I would like to discuss with what about steps to design microstrip patch antenna. So first we need to design the antenna, whether it is an ultra wideband antenna, whatever it may be. You need to first design the patch and the ground on top and bottom side of substrate, and then we need to apply feed to the feed structure. So for that purpose, in this case, I have to take in a waveguide port to the face of the feed, and it is important we need to get impedance matching, otherwise the antenna will not radiate much energy into the free space. For that purpose, a 50 ohm microstrip feed line is to be taken, and to achieve 50 ohm microstrip feed line, we are going to consider the waveguide port dimensions like this. So once you have selected this phase of the feed, it will ask you the waveguide port dimension in the software there. So such type of window has been appeared, and there we have to produce the waveguide port dimensions like X minimum, X maximum, Z minimum, Z maximum. So the formulas for applying X minimum, X max, Z minimum have been given here. Here, X minimum is to be selected as 3 times to width of the feed, and X maximum is also 3 times to width of the feed have been selected, and Z minimum is to be taken to be twice to the value of height of the patch plus height of the substrate, and that the maximum is to be taken as 4 times to the height of the substrate. So here WF is width of the feed, H sub is height of the substrate, HP is height of the patch. So that depending upon how much width you have been taken for the feed, appropriately you can assign the port dimensions here and try to simulate the design. Then you got the results like we have to observe the results like S11 impedance. We have observed radiation efficiency. We have to observe total efficiency, impedance plot, real impedance, imaginary impedance in one-dimensional result pane, and to observe frequency versus gain plot, we need to do some more simulation in addition with the previous, with the help of template-based post-processing in the old CST version, and right now it is modified as result templates. So to obtain frequency versus gain plot, we need to follow these steps. So I would like to show you all these steps in the hands-on experience session. Now, what you need to do for obtaining this gain plot is go to simulation, then click on field monitor, check the radio button, far field RCS, and then check transient broadband, click on OK, run on simulation, then go for result templates. There we have add new processing step is there. Select far field and antenna properties and far field result. Select maximum gain over frequencies, click on it, and then go for evaluation. You got one-dimensional result of gain plot, which is to be noticed at the bottom side in the pane tables. Similarly, we need to obtain the radiation patterns. And these radiation patterns have been either E-plane and H-plane. We need to get E-plane radiation patterns have been obtained by choosing the value phi equal to 0 degrees, and H-plane radiation patterns have been obtained by choosing phi equal to 90 degrees. Again, you need to go in the simulation software, either simulation and field monitor. You have to check far field result RCS, and then assign frequency where you need to get those radiation patterns. Say, for example, in ultra wideband technology, say if you are going to get 3 resonant frequencies, go with those 3 resonant frequencies. Those 3 resonant frequencies you can simulate the design by making use of far field. Then you get the radiation patterns associated with those 3 frequencies. Then for each associated frequency, you need to get E-plane radiation pattern by setting phi equal to 0, and H-plane radiation pattern by setting phi equal to 90 degrees. Then plots will be observed there. Then you can have to observe those radiation plots. And this is my Google Scholar citations. As of now, I have 250 number of Google Scholar citations with H index of 9 and I-10 index of 9. And if you have any queries, just contact with me. Myself, Dr. V. Koteshwar Rao. My WhatsApp, mail ID, official ID, and the college ID have been given there. For all the researchers who are initiated towards research antennas by making use of CST, you are always welcome. And also collaborators, those who are working to collaborate, you are always working with me. Thank you. So after this session, I would like to go for, after a small break of 10 minutes, I would like to go for those designs, how we can design ultra wideband antenna by making use of computer simulation technology. Thank you.
Thank you, sir. Thank you for your such a informative session on introduction to transmission line parameters, UWB antennas and applications, and CST software introduction and design specifications of various antennas. So I request all the participants to have a 10 minutes break, and then we will continue the hands-on session after the break. Thank you.
Thank you, sir.